In this Blackboard session, I'm going to show some of the main properties that makes the multivariate Gaussian a very nice distribution to work with. And some of those properties are its independence properties and linearity properties. So let me first look at independence. So let's say I have a Gaussian distribution, Gaussian in two variables x and y. Both x and y can be scalars or they can be vectors. X has an expectation A and y has an expectation B. And then they have a joint covariance matrix that has this log diagonal or diagonal structure, capital A and capital B. And then my claim is that this is the same as making a product of two Gaussians that looks like this. One Gaussian in x. Expectation A, covariance uppercase A. And then another Gaussian in y. Expectation lowercase b and covariance capital B. So this is my claim. So how do we show that? The key here is to keep in mind that the multivariate Gaussian is given entirely by the quadratic form in the exponent of the exponential. And for this Gaussian on the left-hand side, the quadratic form, it looks like this. So we have x minus a, y minus b. This is transposed. And then I have the covariance matrix inverse. And x minus a, y minus b, not transposed. Okay. Then I need to manipulate this a little bit. So the covariance matrix I'm going to invert. That's a diagonal or block diagonal matrix, meaning that I can invert the blocks separately. Then this last vector I don't do anything with yet. X minus a, y minus b. And then what I need to do now is I multiply this one with this and this. And this one goes together with this and this. There are no cross terms, so I never need to multiply this one with this one. And then end up with this x minus a transpose, capital A inverse, x minus a, y minus b transpose, capital B inverse, y minus b. This is basically the proof, because what I have shown now is that the exponent is now of the left-hand Gaussian is actually a sum of two different quadratic forms, one in x and one in y. So when I take the exponential of this, I get the product. So of these two, so the first term in the product would be a Gaussian in x. The second term in the product would be a Gaussian in y. So when I have such a product, then they are independent. And then I'm going to look at a very nice formula for linearity of Gaussian random variables. So let's say that just call it f of x. It's Gaussian in x. The expectation a and the covariance capital A. Then I make another variable y, which is matrix capital F times x. And then my claim is that this means that the distribution of y is also a Gaussian in y with expectation fa and covariance f capital A, so capital A, F transpose. To show this result as general as it can be made is a little bit complicated because I would need to use something like moment generating functions in a vector case. So to keep this relatively simple now, I want to restrict attention to the case where the matrix F is invertible. So that's a special case, but it's an important case and it shows the general structure of how this works. So let me just restate what I have. X, I said that one is distributed according to something that is proportional. So then I use this notation. Proportional to exponential of minus 1 half x minus a equals a x minus a plus x minus a. Okay. So what I'm then going to use is the general formula for nonlinear transformations of random variables. So remember I did that when I went from a Gaussian random variable to looking at what is the distribution of the square of them. Here I have a linear transformation, so that's a special case of a nonlinear transformation. Then I know that the distribution of y according to that formula. I'm going to look at solutions of this with regard to x. Clearly there is only one solution when f is invertible, that's x equal f inverse times y. So then I'm just going to insert that in this thing. Then there is this Jacobian term that I should deal with too, the absolute value of Jacobian, but that's going into the proportionality constant, so I'm not going to worry about that. Then I have of course minus 1 half, but I have now f inverse times y instead of x. So then I have already an expression for the distribution of y, which clearly is some kind of quadratic form in y. Exponentiated, so I know that this is also a multivariate Gaussian. But I want to find what is its expectation and covariance, and then I need to do some manipulations. So I'm going to do a little trick. First, I keep this as it is, and then I want to get this f, to get it out of there, and I want to get it, well, somewhere else than in the random vector slot, possibly into the covariance matrix. So let me write it like this now. I simply insert an F transpose here, F transpose inverse, because I know this is going to work. And then I have A inverse, and again F inverse times F. F inverse y minus a. Okay. Now you see that this thing I can probably cancel with this thing. I should be able to do something similar on this side. So I'm going to be left with this one here, and I'm going to be left with that one here. Let me spell it out. So while this thing cancels here it does not cancel, so I get this FA. Then I have a similar situation on the other side. So I'm kind of done with what happens inside this parenthesis. For the covariance, I can do a little bit more. So this thing here is the same as this. You can just look at this with standard rules for matrix inversion and you'll see that you end up here. And what isn't here, that's precisely what you have here. And this is my new expectation, which is what I have here. So then we have verified that at least when F is an invertible square matrix, this very nice result for linearity holds.